Welcome students. In our last session, we learned that an equivalence relation is one that is reflexive, symmetric, and transitive. But here's the most powerful outcome of such a relation. It naturally divides a set into distinct groups, where each group is called an equivalence class. These groups don't overlap, and together, they cover the entire set. This process is called a partition of the set. Let's understand this visually. Let's take the set of all integers, call it Z now, define a relation R like this. R equals the set of all pairs A, B such that 2 divides A minus B. Is this an equivalence relation? Let's check, is it reflexive? Yes, because 2 divides A minus A, which is 0. Is it symmetric? Yes. If 2 divides A minus B, it also divides B minus A. Is it transitive? Also yes. If 2 divides A minus B and B minus C, then it divides A minus C too. So yes, it is an equivalence relation. Now, let's look at what it creates. The equivalence classes 0 includes all even integers, -4, -2, 0, 2, 4, and so on. 1 includes all odd numbers. -3, -1, 1, 3, 5, and so on. So, this relation neatly splits the entire set of integers into just 2 disjoint sets, evens and odds. That's the power of equivalence relations. They group elements that behave the same into well-defined classes. Now, here's the connection. The collection of all equivalence classes of a set under an equivalence relation is called a partition of that set. That means every element of the set belongs to exactly one equivalence class. The classes are mutually disjoint, no overlaps. Their union gives the entire set. Let's take the set of all integers Z and define a relation R as R equals all pairs A, B such that 3 divides A minus B. This relation is also an equivalence relation, and guess what? It splits Z into 3 equivalence classes based on remainders when divided by 3. First, the equivalence class of 0. It includes all integers divisible by 3, -6, -3, 0, 3, 6, and so on. Next, the equivalence class of 1. This includes all numbers that leave a remainder 1 when divided by 3, like -5, -2, 1, 4, 7, and finally, the equivalence class of 2. These numbers leave a remainder 2, like -4, -1, 2, 5, 8, and so on. So this relation divides Z into 3 clean, non-overlapping groups based on how each number behaves when divided by 3. Let's take the set A of 1, 2, 3, 4, 5, 6, 7, a simple set of the first 7 natural numbers. Now, define a relation R on this set. R includes all pairs A, B where both A and B are even, or both A and B are odd. Let's check, reflexive, every number has the same parity as itself. Symmetric, if A and B are both odd, or both even, then so are B and A. Transitive, if A and B are odd, and B and C are odd, A and C are odd. So, R is an equivalence relation. Now the equivalence classes are the equivalence class of 1, and it includes all the odd numbers in our set, 1, 3, 5, and 7. The equivalence class of 2 includes all the even numbers, 2, 4, and 6. These form a partition of the set A into 2 non-overlapping groups. Each equivalence class is one of these groups. The whole set breaks down into these cleanly separated pieces, like slicing a pizza into perfect slices with no overlap and no leftovers. This idea of partitioning helps us organize data, solve classification problems, and even underpins ideas in modulo arithmetic, geometry, and more. Now it's time to test yourself. Let's take the set A of 0, 1, 2, 3, 4, 5, 6 and define a relation R like this. Set A, B belongs to R if A is congruent to B modulo 3, which just means the difference A minus B is divisible by 3. Step 1. Is this an equivalence relation? Let's check. Is this reflexive? Yes, because A is always congruent to itself. Mod 3. Is this symmetric? Yes. If A is congruent to B mod 3, then B congruent a mod 3. Is this transitive? Yes. If a congruent B and B congruent C mod 3, then a congruent C mod 3. So yes, R is an equivalence relation. Step 2. Find equivalence classes. The equivalence class of 0 equals 0, 3, 6. The equivalence class of 1 equals 1, 4. The equivalence class of 2 equals 2, 5. Step 3. Check partition. Classes are disjoint and their union equals A, hence they form a partition. An equivalence relation is reflexive, symmetric, and transitive. It leads to the formation of equivalence classes, subsets where elements share a defined property. These classes are disjoint and exhaustive, forming a partition of the set. Understanding these structures enhances problem solving in modular arithmetic, classification, and mathematical reasoning.